If artificial intelligence vanished from our world tomorrow, you might expect chatbots to go silent or image generators to stop working. But for modern software systems, the impact would be far more catastrophic than a simple feature outage. The very logic that powers your search results and personalized feeds relies entirely on an assumption of infinite compute power and instant inference speeds. If AI disappears today, it does not just slow down. Our core infrastructure collapses because the decision-making code we built decades ago has been replaced by probabilistic models running in real time. We have spent years treating artificial intelligence as a layer we can add to existing applications or turn off with a feature flag. The reality is that modern engineering architecture has been rebuilt from the ground up on top of this new capability. We are no longer writing static instructions for computers to follow. Instead, we have designed systems where the logic itself is ephemeral, generated only when an inference engine runs. If you remove the model, you do not just lose a feature. You erase the operating system's ability to make decisions, leaving behind empty shells of code that cannot function without their probabilistic brains. This shift marks what researchers are calling the end of traditional software engineering as we knew it since the 1960s. For generations, engineers encoded deterministic rules into permanent files. If this input occurs, execute exactly these steps to produce a specific output. That logic was static and reliable. Today, that paradigm has flipped. In systems built for search engines or recommendation feeds, there is no longer a hard-coded set of rules buried in the source code. The decision-making process happens dynamically during execution loops. Code is now just an ephemeral byproduct generated on the fly to facilitate communication with these models. If you strip away the AI layer, that logic vanishes instantly because it was never written down anywhere else. There is no backup plan, no fallback static version of the codebase to revert to when the power goes out or the servers crash. Quick resource note. I keep a curated set of Amazon search links in the description for books, gear, and tools relevant to this channel's topics. Some are affiliate links, so I may earn a commission at no extra cost to you. Please consider supporting the channel by using those links if you find something useful. Consider how search engines and recommendation algorithms have fundamentally changed in just a few years. The shift has moved us from simple retrieval systems to what experts call generative information retrieval. In the past, if you searched for a product, the system would retrieve existing links matching your query based on keywords. Today, these systems are architected around two new pillars: information generation and synthesis. They do not just find answers, they construct tailored responses in real time by integrating vast amounts of external knowledge through complex probabilistic reasoning. The critical vulnerability here is that our entire infrastructure assumes high inference speed and low cost as constants. We design for the assumption that an AI model can instantly synthesize a personalized answer from billions of data points without breaking a sweat. But this architecture masks a single point of failure regarding latency and compute costs. Standard software scaling rules, like adding more servers to handle traffic spikes, cannot replicate the speed or efficiency of specialized inference hardware when models disappear. If you try to revert these systems to deterministic logic during an outage, it is impossible in real time. The system does not degrade, it fails fundamentally because it has no mechanism to synthesize data without that model acting as the processor. This fragility extends beyond just code and servers into human behavior itself. We are seeing a profound feedback loop where users have begun optimizing their decision-making around these algorithms, treating them as infallible predictors rather than tools. In behavioral studies involving over 1,300 participants, more than 40% of subjects surrendered guaranteed rewards to align with AI predictions. They began making choices based on the belief in predictive authority rather than actual outcomes, reducing their earnings by nearly 43%. This means that if the system vanishes today, it breaks not just the service you are using, but also your ability to navigate digital environments effectively. Users have been trained to rely on these outputs as a substitute for their own judgment, creating a dependency where removing the AI leaves them unable to make sense of the information presented. For developers and engineers listening closely, this is a critical career reality check. You may be building systems that treat artificial intelligence as just another API call or optional module. But if you do not design with a deterministic fallback in mind, your architecture has a fatal flaw. It relies on an assumption that AI will always be there to provide the core logic. The next generation of engineering is not about learning how to use models better. It is about designing resilience for the moment they fail. We are moving from writing static code to orchestrating reasoning engines. And if your skill set only covers traditional coding without understanding these new architectural dependencies, you risk building systems that cannot survive a shift in capability or cost. The lesson here is not fear of artificial intelligence, but a realization of how fragile our current digital foundation has become. We have built the world's information access layer on an assumption of infinite compute power and instant inference speeds. If that changes due to hardware constraints, energy limits, or model failures, we do not just face slower load times, we face a complete cessation of service for search and recommendations because the logic required to run them no longer exists in static form. True engineering resilience requires us to start designing systems that can function without this assumption, ensuring that when the models stop talking, our infrastructure does not go silent with them. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.